for fun. Actually, I hope you will enjoy it. Okay, so what I wanted to draw on the board. In the meantime, I forgot it. Yes, so the functions, I would call them waves, can be decomposed as sum of I call source waves, but here in this form it's exponential. Actually, sinus is the result of a special form of exponential. This formula is called Fourier series, and this partial stuff, which is not infinity, just a part of this sum above, called Fourier sum. And here the important thing are the coefficients. So if you are lucky, then you could have everything. You have a square signal, and you can decompose it, or you can compose it. The typical stuff is the synthesizer that I always tell you. You have a synthesizer, it's like piano, and it could give sound like a piano, or like a violin, or an organ, or whatever you want. Or you have a measurements, and you can do a lot of things with it. For example, this noise filtering that will be the top of this class, actually, noise filtering, is easy if you can do Fourier transformation. The Fourier transformation formulas are continuous, and they are for function. But in the nature and in the reality, you have just signals. But we will far beyond of this, because we start from linear algebra, and I never thought that we will reach this this stuff. I skip proof and deductions right now. I don't feel sense to teach you deduction in this topic, and sometimes I don't feel a sense to teach you some part. The problem here is that I skipped some very serious parts, very complex stuff. Do you know Penrose? Penrose. Have you ever heard of Penrose? Penrose. Penrose. It's not the right pronunciation, perhaps. Do you know Stephen Hawking? Yes. Penrose is as smart and as famous cosmologist like Stephen Hawking was. But when I looked into deductions, I learned his work. Recent work, so he's a living, alive mathematician, cosmologist, and I don't think so that that part of the linear algebra you should learn. For physicists, for IT guys or engineers, I would teach it, but for you chemists, I would not. Okay. This statement says what I explained you in the last minutes. You have the Fourier stuff. You have an interval from 0 to 2p. Okay. For you, sorry for the question, you know what is radian. Because the Hungarians didn't know 1 year ago. They didn't teach. I know it, but they changed what they learned at the secondary school. You know radian. Okay, so if you know why is this from 0 to 2p. So this is one interval of a periodic signal. Yes. So it's 160 degree. Sorry for the question. Sorry, actually, so I don't. Okay, what I said, 360. I wanted to say 360, sorry. Okay, so you divide this into intervals, and then you have a matrix. And that's the so this is about existence of this Fourier sum. This more difficult. You have an integer. You have this epsilon. Is it right pronunciation? Epsilon and omega. Omega numbers. Important thing. There will be two things with the. This is very far from the practical Fourier application right now. This is a pure mathematics, not pure but something mathematics. There are the normal ranges, and there is so-called frequency ranges. You have the waves, everything, and then you do Fourier transformation, and then you go to the frequency range. I will show you examples. This is not the part that is easy to understand. Okay, great. So you construct from the Fourier sum a matrix. I will show you this matrix very soon. And this matrix actually there are two, have the following properties. These matrices, the one with epsilon and the one with omega, are conjugate to each other. Do you remember what is conjugate? You have a complex number. Do you remember complex numbers? It has a real part and an imaginary part. The conjugate changes the sign of the imaginary part. Conjugate is A minus B. That's it. Or if you use the trigonometric stuff, this is the real, this is the imaginary. You have this vector, and this is C. Actually, this is A and this is B. Then the conjugate is this. This A and this is minus B. It's okay? And in matrices, you conjugate the elements. That's it. It's not simple at all. This is too difficult. You cannot talk about impedance and capacity without complex numbers. But you are not a physicist. Do you know this? You know what's this? It's impedance. You have a, what is the name? This hub. What is toroid? It's like an antenna. You have a wire, and it looks like this. What is its name? Coil. Thank you, coil. And this is a couple. This is the impedance of coil, and this is a capacitor. Do you know what's capacitor? When you can accumulate charge with normal with DC, and with AC it has a it has a resistance, and this is for complex numbers. You cannot talk about this without complex numbers, but this is not thing that you should know. So I erase it. Okay, so okay, this three stuff is about the properties of Fourier matrices, properties of different rows, and also some stuff about the matrices. These are unitary matrices. It means, there are matrices which are orthogonal, and we define the conjugate transpose of the matrices previously, and if a matrix is equal to its conjugate transpose, then we call them unitary matrices. Doesn't matter. This, I will not ask this. This is now it's better. This kanjis or hieroglyphs are this. You have a matrix. The matrix has this form, and you can use this matrix with a matrix operation, matrix multiplication on a vector, to get its discrete Fourier transform. You have this. You have this matrix. Okay, this is okay. If you have these samples in a vector, you have this transformation, you can do an operation called discrete Fourier transformation. That's a linear mapping. It's linear, so that's why we talk about here in linear algebra, and actually that's it. You can change the direction. You can do an inverse stuff. The original task is you have n linear independent function. You have some points in some and some values, and you want to get the values of that point from the sum of the linear independent functions. This problem is now the opposite. You have the points, and you want to get the functions. Actually, the functions will be something A-led stuff with a constant. Okay. This stuff, not the above, below, is noted by Fn, and this is called discrete Fourier transformation, and this is a linear transformation, linear mapping. Yeah. You can write this for coordinates, and then you move from coordinate space to wave space. This is how we say it. And with coordinates, you can use this function. This is nothing more, just a matrix, a very special matrix product. Usually, which are here in this region, we use small letters, and for this we use capital letters. Honestly, in practice, we use here coordinates, and instead of this, we use what is the name? Omega waves, frequencies. Okay, this Fn, n is a number, has different forms. Okay, this is bad, this should be a different form of brackets. F1 is this one, F2 is this one, F4 is this one, and this monster is F8. You don't need to know this, you should use software for this. Okay, this discrete Fourier transformation has some properties. This is, okay, I say transformation, and transformed constant vector is in this form. And you can do the transformation in both directions. I don't know what is the sense of the second, but the last one is very important. You can construct an inverse matrix, and the name of the discrete Fourier transformation inverse is inverse discrete Fourier transformation. This is also something horrible long deduction, so we skip it. Now some example, really just some example. You have a vector, this 1, I, 2. You have, and you have to do this transformation. F4 is given here. Here, you have the vector. You do the matrix multiplication for each row, and then you get this vector. That is the discrete Fourier transformation of this vector. And this is what you already know. In technical applications, you use this filtering. What it does mean? It means that you have different algorithms to calculate Fourier transformation. Some of them called fast Fourier transformation, that's the definition at the end. It's costless. I mean not costless, it's quick. You can do it quickly. Then you can do the following. Use this discrete Fourier transformation, do the so-called filtering, and then do the inverse discrete Fourier transformation. This filtering could be a mapping vector. For example, you cut some frequencies. What I showed you about early disk previously, that's in astronomy, it's a method to cut the top, the bottom of the frequency spectrum, and then you got the something which is filtered, and then you do back the inverse discrete Fourier transformation. Okay. the Fourier transformation is a matrix multiplication, and it requires n squared multiplications. If you have an algorithm which is faster, for example, in this n log n, that's the speed, it means you have, for example, a matrix, and the matrix is 8 times 8. Then you need something, some number of operation, it's 46. But if you have something, an ID, for a numerical algorithm that allows you to do it something, it's less than 8, it's 6 or something like this n log n, then we call that algorithm is fast Fourier transformation. That's an algorithm. Okay, there are mathematics. You can prove this fast Fourier transform, FFT, exists. Okay. This is the convolution, discrete form. You have two vectors, actually two functions. This asterisk is the symbol of convolution, and you can calculate the convolution with this sum. You can do the following. You have these two functions. You do the fast Fourier or just discrete Fourier transformation. Actually, the fast Fourier transformation is just a fast algorithm for discrete Fourier transformation. And then you move from the coordinate space to frequency space. And then the convolution is just a simple multiplication. You do not need to do this sum for each pixels. It's just one operation. So you spare time and computational capacity. And then when you're ready, then you do back the, you undo the Fourier transformation with the inverse fast Fourier transformation. And then we are happy. Okay, this, what I said you, it was quite quick and very confusing. Absolutely confusing. I know very well, don't worry. That's why I told you I will not tell you this. Not ask in the test. But for example, more examples necessary. Yes, and yeah, I like it. Oh. Great. Fine. Great. it moved to my cell phone, so now we have normal internet. Okay, so okay, you you have a measurement, for example, radio noise or something like this. It looks horrible. It says nothing, I think. It has amplitude, you have time, great. Then you do the Fourier transformation, and then you will find special frequencies. Okay, everything that I told you is something in the cloud, because the mathematical form and the practical form is far to each other. So you do this transformation and you will see that there are special frequencies. If you want to filter, for example, then you somehow remove these frequencies. Just put a function, for example, a step function, which is 0 until, for example, 25 hertz here, and then do back the transformation, and then you removed the low frequencies.
I think when we do measurements with different instruments in the lab and we take our graphs, our data, and we check all the noise and we click just normalize,
Yes.
all
Yes.
The normalize button is the Fourier, doing a Fourier transform, I think.
Then it cut something and did the inverse. What measurements was it?
Well, we've done many. We did mass spectroscopy this week. Last week we did gas chromatography.
But what level is this?
What lab?
What lab? Yes.
The analytical.
The
analytical chemistry.
Analytical chemistry. And what instruments do you use?
High pressure liquid chromatography, gas chromatography, mass spectrometry. I can't say it. Capillary electrophoresis. All of these give us graphs where we have a lot of them have noise, and our signals, and we have to normalize graphs.
This is very serious. So these are very expensive instruments. Are they new or older?
Some of them are really old, and some of them are newer. Some of them we got from Sweden. Actually, one of our analytical chemist professors, he worked in Sweden, and they donated a bunch of machines here, I guess. Yeah. So we have a lot of machines that we use.
This is useful, this part. The Hungarians told me the first labors, the evaluation of the measurements was made on paper.
Yes.
Do you still do it?
Well, sometimes we'll have to graph on paper our data, but we have all the machines to do it for us. But but sometimes they want us to do it on paper just for practice.
Do you use Mathematic or Maple or MATLAB or something like this?
No, we haven't. I know we learned last Friday about R.
That's great.
Yeah.
R. So you just learned.
Yes, and our professor in our geometrics class, he talked about using R to do.
Is this the Gabor Lanteri?
No, it's Bellinger Attila.
What Attila?
Bellinger.
Bellinger.
Bellinger Attila. He's the head of the PhD chemistry.
Okay, that's good. Yes, the R is good.
Yeah.
What development environment did you use?
He showed us how to do like the inverse, what programs and how to do an inverse of a matrix and the transpose of a matrix.
But what was the environment? Did you use only command line?
I think so. I think just what do you mean by environment? Like the I don't know.
Okay. I check whether I have it or not. Perhaps. So this is not my computer. This is my working computer. I check whether I have.
Our data was different absorbance values versus concentration of solutions that we're measuring.
I just can show you this. No, sorry. This. You can do everything in a command line. I show you. Oh, if I can. Okay, this is a command line. You can write different things here. Did you use something like this?
Yes. Yeah.
Oh, that's the simplest. Then just you use the R in this environment, because there are usually an editor which gives you some colorization of the source code. It helps you to interpret and understand, and also it couple together the different files if you have more. This is PyCharm. The R Studio. R programming language. You didn't. Oh. Where is it? Oh, no pictures. Sorry. So,
Should I switch to Monday?
I didn't know that it's a video. That's better. So you didn't see something like this?
No.
With this, for example, you can check the value of the variables, or you can run the code step by step. It's easier to debug and it's easier to develop with it. But it's not obligatory, just it makes your life easier. The R is a good language. It's very good for statistic. I have a very little knowledge about it. With what is the name? Not Udemy, but I cannot recall the. So there are apps where you can learn Python and R. And R is good in science. Okay, so where we were. Okay, here, Fourier transform. Other examples, better examples. This is really nice. This is what I'm talking about. Look, so here you have a square wave. In all processors, all the digital stuff, you have this square wave, and naturally the square wave is not is made directly. They put together from sinus waves because it's easier to construct sinus waves. If you do the Fourier transformation, then you will find the functions, the sinus functions with appropriate coefficients to get this square wave. This is the meaning of Fourier transformation. But this is not the discrete stuff. This is the continuous stuff. But the funny thing is that it doesn't exist in reality. Everything is discrete. You cannot measure continuous functions. You just have discrete points. Okay. You don't learn electronics, of course, not. The physics student who is not here, and I don't know how he will finish his studies in this year, doesn't matter, should learn electronics. There, it's a fundamental process. It's to create a low pass and high pass filter. It means you have different frequencies, and then you have a filter. It's from fortunately, I cannot do it anymore. But the filter allows to pass the low frequencies for low pass filter and high frequencies. And with Fourier transform nation, you can do the same. You have this filter. In frequency spectra, it looks like oh, like
I think maybe we mentioned low and high pass filter.
yes, yes. And this is how you filter the noise.
And
So
you can move the.
can you see at all what is on the screen? So you have the data. The data has different peaks, and you filter only these two peaks. So this is also convolution again. I would look for a better example. Oh. And there are a lot of research to find a better way, faster way to get this fast Fourier transformation and convolution. There is even a book from this. Okay. IRAF, IRAF is a very old tool for astronomers to reducing and do photometry with astronomical images. It has a special file format, very large. You need a fast computer to use it. Preferably, it is on Unix systems. I look for some example, but I find something else. You have this wave set, and the measurement is on the left side. On the right side, if you do the Fourier transformation, now it's not discrete, just any Fourier transformation, and the other thing that you will see in the frequency domain, not range, domain, I'm idiot, sorry. Yes. I feel guilty actually because I not always use the appropriate terms, English terms. Not really, I should prepare better, but well, you still my laboratory rat, so this is the first when I use this when I teach this class. So time domain and frequency domain, not coordinates, time domain and frequency domain. In the frequency domain, the same waves are the information is in the graph. All information that was original in the time domain on the right, but you see only two peaks at the frequency of the measurements. And this is an example how to put together sinus forms. The first is just a sinus. Then you add another sinus, and you almost get the square wave. This is, I have shown you this. And this is what you have seen. You have something, and here it's artificially you add noise. The noise frequency typically higher than the sign, the measurements frequency. So what you do, you transform this to with the fast Fourier transformation. You have the noise and you have everything, okay? And then you cut everything and you only keep these peaks. And you do the inverse Fourier transformation. So then you will have these signs, but this sign, you see, this is the sign right now, and after fast Fourier transformation, cutting the noise, you got this. And that's why you need fast Fourier transformation algorithms, because you use it in real life. I don't know now the situation, but you can do fast Fourier transformation with the lenses. And at the Technical University of Budapest and the University of Szeged, there are expert physicians with optics knowledge. And for example, it's not rocket. What is the term from Tomahawk? It's not a rocket. It's something wandering missile. No, I checked in Wikipedia. Just wiki. Cruise missile. This is you launch it, and it could go and fly very low, slowly, and even it can follow the surface. And to do this, they do Fourier transformation very quickly. And because they don't They are not sensitive for money. But they're sensitive for time. They use lenses. At least they used a few decades ago for Fourier transformation. And somehow it recognizes the surface and follows it. But the example is that it uses lenses for fast Fourier transformation. Not fast Fourier transformation. But it's fast, of course, because it's run time, so the lens can process the image very quickly. Of course, it's very expensive, but who cares when $1 million for a cruising missile is cheap. Okay, so that's it for today. This was for fun, actually. And we will have class today. Then there will be the Easter holiday. And during the Easter holiday, I will give you homework, and we can discuss it at the last class, and then you write the test. I hope with very good results, and I can give you stuff, and then I have to give you a list of thesis or something like this. But the exam will be a written exam.